Alright, first let's visualize what this inscribed cone might look like. Maybe the cone's radius and height is the same as the sphere's radius. Or maybe the volume of this cone is more. Now the radius of its base is smaller than the radius of this cone's base, but we have a much longer height. Maybe that will cause us to have a bigger volume. We could take an extreme case of that, where the height of the cone is really tall. So maybe that will maximize the volume, except that our radius is getting really small. So let's find the maximum volume of the cone. What is the one variable that's changing? It's this, which is the height of the cone minus the radius of the sphere. That's the part that changes. That's our one variable that our volume for the cone is a function of, which is 1/3 times the area of the base times the height of the cone. So 1/3 times the area of the circle, the base of the cone, we can't use little r because that's already used for the sphere. So for the circular base, I'll use capital R. So pi r squared, and then the height of our cone is x plus r. All right, so remember r is a fixed constant for our given sphere. Our variables are capital R and little x. So I'm going to choose to make volume a function of this unknown variable, and we'll rewrite capital R in terms of the one variable x and maybe the constant little r. All right, here we go. Let's write another radius of the sphere, which is r, and then we can solve for capital R using the Pythagorean theorem. So using the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared, so that capital R is the square root of little r squared minus x squared. We'll square that, and we have our volume function. All right, so volume is a function of one independent variable, x. R is a fixed constant. To find the maximum volume, we'll set the first derivative equal to 0 and solve. I'm going to isolate that factor and find the derivative of the product of these two functions using the product rule. Derivative of the first function times the second function plus the derivative of the second function times the first function. Set that equal to 0. Distribute. Combine like terms. Get the constants on the right side. Keep all the terms with x's on the left side. But that's not going to work because we have a quadratic. So we'll have to keep all of our terms on one side and maybe use the quadratic formula. Ax squared, bx, and c. This one actually is factorable. If you multiply this out, this is equal to that. So if it factors and the product is 0, then one of these factors must be 0. All right, so clearly this makes no sense. So our only critical value is x equals 1/3 of the sphere's radius. So the maximum volume will be 1/3 pi times the radius, which is r/3 squared, multiplied by the height of the cone, which is x plus r/3 plus r. There's two ways we can show that this is where there's an actual maximum volume with the first derivative test. The number line represents the x values, and r/3 is our critical value, so something smaller could be anything, like maybe r/10, and something bigger could be r. So we can show that when the radius is r/10, v prime would be equal to something that was positive, and when it's something bigger like r, v prime will be negative. And by the first derivative test, therefore, we have a relative maximum at r/3, whereas a second derivative test would look like this. First derivative, second, I combine like terms right there. I distributed and combine like terms. Second derivative at our critical value, which is negative 4 pi r/3, which is negative, and by the second derivative test, therefore, we have a relative maximum. All right. Let's see, 5 minutes or so to explain this problem. Hopefully that helped a lot and it makes sense.